Hey everybody, this is Miss Fisher. I will be recording your lessons for Unit 1. So if you really liked Miss Willis, I'm sorry. She's gone for right now. You'll just have to have her in class. We are going to be reviewing our 12 basic parent functions. And as it says on your paper, you will need to know the name and the graph behaviors for all 12. So I want you to pause the video right now and see how many of the 12 you can do. And then unpause and see if you got them right. Okay, welcome back. Let's see how you did. This first one is a linear function. And we like to call these the parent functions, we like to call them the mother functions. They've not been shifted, so they are the no-shift mother functions. The first one is linear. The second one is quadratic. Hopefully you guys got those two right. The third one is your basic cubic function. And a lot of you from Math 3 are like, hey, I thought this looked like an N shape, and you would be correct in thinking that, but that's only when you have other things added in, like all of this jazz, something like that. But if it's just the parent function, then it looks pretty basic, no humps. All right, number 4 would be radical. It starts here at 0, 0. Number 5 would be logarithmic. And that is worth noting that has a vertical asymptote here at the y-axis. You could also say y equals log x. Number 6 is a radical function. That has a vertical asymptote at the y-axis and a horizontal asymptote at the x-axis. Okay, number 7 is exponential. That doesn't have to be e to the x. That could be 2 to the x. It could be 10 to the x. It could be 1,000 to the x. It can be whatever you want. But they all have general shape that's the same and a horizontal asymptote here at the x-axis. Number 8 would be the absolute value function. A lot of people have been asking me, where do I find that in my calculator? If you have to graph it in your calculator, you find that in the math menu, or you can find it in the catalog. It's the first thing in the catalog. But again, that starts here at 0, 0. Number 9 is something called the logistic function. That is something that is brand new to you right this second. It doesn't have to have an e to the x in it. The other version would be 1 plus b to the x. But it's worth noting for this one that it has two asymptotes. In the parent function, it'd be y equals 1 and y equals 0 are the two horizontal asymptotes. We'll talk more about that later this unit. Number 10 is the sine function. Number 11 is the cosine function. You need to know the difference between these two. One is at the the y-intercept is at 0, 0 for sine, and it's at 0, 1 for cosine. Okay, number 12, the last of the basic functions, is the greatest integer, or we call that the step function. Okay, because it looks like steps. That's a special case of a piecewise function. All right, this next section we are not going to spend too much time on right now in the video because you need to use a calculator, and I cannot show you a calculator on our handy dandy little video here. But we have talked about this before, our local and absolute extrema we talked about in Math 3, so we'll go over that in class. All right, stretches and compressions. So I like to call the shrinks compressions, but you do you. So this is basically, if you start with f of x, it's all about multiplying f of x or multiplying the x. So if it's horizontal, like it says here, anything that's a vertical change to the graph is a result of a number that's on the outside. Anything that is a number that is inside the parent function will be a horizontal change to the graph. And that's true when we are shifting up and down. It's true if we were shifting left, right. Okay? So that's going to be the same for the stretches and compressions. Now, I have to always do this kind of visualizing, like literally stretching or compressing the graph with my hands. So the other thing that I try to remember is that anytime there's a number greater than 1, that is going to make your graph physically look skinnier. Any time there's a number less than 1, and we're not talking about negatives, we're just talking about a number between 0 and 1, like a half. Anytime you have that, your graph is going to look wider. Okay, so starting with horizontal, if you have f of kx, and here the k is a number that is greater than 1, that is going to make your graph look like it is skinnier. So if it looks skinnier, I have to think about what do I have to do to my graph physically in the horizontal direction to make it look skinny. And so I think about actually pressing that together. So I have compressed it. I've pressed it together. So that is a horizontal compression. All right, if I multiply it by a number that is between 0 and 1, that's the visual effect is that it's going to be wider because that is a number between 0 and 1. And so horizontally, to make my graph look wider, I have to pull on it. So that is a stretch. It's a horizontal stretch. So vertically, the number is going to be outside the function. So if I multiply by a number greater than 1, it is going to make the graph look skinnier. So I have to think about vertically, what would I do to the graph to make it look skinnier? I would pull on it up and down. So pulling on it is stretching it. So that is a vertical stretch. If I multiply by a number between 0 and 1, that's going to make it look wider. And so to make the graph look wider, I have to press it together. I have to squish it. So that is a vertical compression. Okay, so for this first example, it says find the equation of the graph if it undergoes the following transformations. So a horizontal shift 2 units to the right, I would have to do f of x equals, and actually let's be a little bit more precise. 2 units to the right means that you would do x minus 2. So the result is this. A vertical stretch by a factor of 3 means you're going to multiply your function by 3 on the outside. And a vertical translation 5 units up. So you're going to take everything you just did and add 5. So your resulting function looks like this. So that's your answer. All right. So let's skip down to even, odd, or neither. Fun things. All right, we've got a very technical math definition here for you. An even function, all of this has to do with symmetry, by the way. Symmetry. Okay, an even function is basically when you have y-axis symmetry. So it's when your graph is unchanged when you reflect it over the y-axis. So I'm going to give you a great example by moving back up here and looking at the absolute value function. So y-axis symmetry basically means that when you have a number on the right, like take the point 4, 4, that when you flip it over the y-axis, that point will still be on your graph. So, negative 4, 4. Now, algebraically, like it says down here, the rule is f of negative x equals f of x. So what that's saying is that when x equals 4, you get the same y. Look at that. You get the same y as x equals negative 4. And that's what we just saw in the absolute value function. For odd functions, odd functions have origin symmetry. Now, origin symmetry is harder for us to pick out. Origin symmetry essentially means that when, it says right here, when we substitute in a negative x, the y is going to change. So if we had x equals 1 and y equals 1, both coordinates change signs. Because both the x is different and the y is different. So let me show you what I mean coming up here. So looking at x cubed, this is a perfect example. When x equals 1, y equals 1. But down here, when x is negative 1, the y coordinate is negative 1. Okay, so this would be an odd function. All right, that one's a little bit harder for you to see visually. That kind of symmetry is basically the same up here in this quadrant as it is down here in this quadrant. That's kind of the reflection. What makes it really easy to tell is if you flip your paper upside down, it should look the same as it did right side up. That's kind of the way you can pick it out. All right, let's come back down here. The kinds of questions you would have to do is like this one right here. Decide algebraically if the function is even, odd, or neither. So you have to use the rules that I boxed in. For even, you look and say, does f of negative x equal f of x? That's the question. So f of x, you already know. It was given to you right here. That's f of x. F of negative x means you substitute in negative x into the original. So for f of negative x, you would take negative x, put it in for the original, and then we're going to simplify. We want to know, does that equal the original, which was x over 1 plus x squared? And if you simplify and they do equal each other, that means that this is an even function and would have y-axis symmetry. So if I simplify the left side, I get a negative x on top. On bottom, I get a 1 plus negative x squared, which comes out positive, because a negative squared is a positive. And on the right-hand side, we still have our original function. Now those do not equal each other, so it's not even. All right, is this odd? Now, in order for it to be odd, we use the rule that we boxed in for odd. F of negative x equals negative f of x. Well, f of negative x we just did for even. I'm not going to redo all that work. I'm just going to write down what I got right here. So just rewrote that right here. Okay, that's the same thing. Negative f of x means take f of x, which is right here, your original, and throw a negative in front. Boop. And now you want to simplify that and see if you get the same thing. Now when you have a negative in front, that's really like saying a negative 1 over 1. So you're just multiplying the top by negative, and then the bottom you're multiplying by 1. And you must see, does the left equal the right? So you get a negative x over 1 plus x squared, did nothing on the left. On the right, you get negative x on top, and then 1 plus x squared on the bottom. And what you see is the left does in fact equal the right, so that means that it's odd. So that means if you graphed this and looked at it in your calculator, you should see that the graph looks the same right side up as it does upside down. So feel free to check that out. All right. And that, my friends, is it for us on the video. We are going to do the rest in class. And this is us because we are happy because this time the video has sound, I hope. And we'll see you next time. Peace.